Okay, so let's see. The first thing is I need to post the regression homework soon. It's scheduled. I'm happy to be flexible about this. So let's look at the schedule here. Okay, so let's see, we are here, and regression homework is scheduled to be due Monday, April 11th. So it's again going to be worth 100 points, kind of like, is that? So it's not going to be too as challenging. It's going to be all in MATLAB, but I can basically tell you what to do fairly specifically. So I'm happy to have this due later, but the final report is due here, and I can't move this date so much because I want to do the posters, and I want to make sure you do this before you have to turn the poster outline. So I can't really move this date. So I can have it due later if you want. You can suggest a date. There's another assignment due at the very basically last possible day. And again, this will be half the size of this one. Okay, so if I don't hear any suggestions, I'll keep it Monday, April 11th, but if you have a better suggestion, I can move it. Okay, we'll keep it there, and after you post it, if there's a big discussion to change my mind on this, it'll be out in a few days, hopefully. Then we can maybe we can revisit this. Okay. Okay. Good. So today is kind of our last lecture today on regression. We're going to be talking mainly about a technique called lasso, which is basically a L1 regularized regression, and so there's not a regression. Okay, right, and so what L1 regular at the end of the lecture, but for now it's this technique called lasso, like you're in a rodeo lasso. Although one of the inventors of this refers to it as lasso, I think it's just pronunciation. Okay, so however, the lecture is but also cross-validation, and so it's going to be important in this context as well. Okay, so values of I. So for the first, so this is a column here, and so this column is the first, for the ith row of the column is the first data point. ith row is for the second data point, and so forth. This first column is going to be all ones. So A0 is going to be the all one vector. Okay, and so before we looked at this in 1D, you had this form where we're going to try and predict AX plus B was supposed to be equal to Y. Right? This B is essentially we're going to have two coefficients of this X is actually going to be the data here, but this is one coefficient, this is the other one, but this one was always multiplied by 1, it didn't do anything, and so now this column, which is all ones, is taking care of it. Okay? Oh no, okay, so these are, I screwed up the notation from the notes. These are going to be the coefficients we're going to try and solve. So this expression is going to be very, very confusing. These are the coefficients, and we're going to try and find some function of Fa of pi's. This is yi squared. Now this last term here, this is going to be yi. Okay, so we're going to try and predict this last value using some function that depends on this matrix A of all the first few values. And this sum is going to go for pi and p. And so these are just the first d plus 1 values. Okay, so what'll be useful is to define this matrix, and this will be the all one vector, and then it's going to have px. And so this part of here, write this in another corner here, we'll call this px here. So this part of this input data for the first v coordinates is going to go here, and then this all one vectors. And so now we're going to have, this expression is going to be to try and find the minimum A so we're going to try and find a vector of coefficients, A1, A0 through AD, where multiply those by x. This is a linear expression here. It's going to try and look like y, which is going to be the last value of each of these data points. Okay, and this is, the norm is minimizing the sum of the square errors. This is, I took a square root inside this norm here, but if you minimize it, you minimize it. The square root is not changing what the minimum is. Okay, so now I mentioned this before, but there's a solution to this, that this vector A, you can write this as A x transpose x inverse x transpose y. Okay, so I can take this data matrix X and convert it by doing x transpose x inverse times x transpose, and then multiply this by the values y, and this will give us the value A, which minimizes this. Yes?
You said y was just the last entry, so is this only minimizing the like distances of like one dimension?
Yes, that's correct. Yeah, so I'm only trying to minimize the last dimension here. Okay, so there are advantages and disadvantages to this, right? The disadvantages, I'm only care essentially about this last coordinate. The advantage, and a lot of you, and I'll get the feedback, I'm finishing the feedback on the projects, the intermediate reports. But a lot of you in the projects are facing this challenge where you have data that has lots of different units to it. It's high dimensional, but each unit is different. Okay, so what's happening is when you only care about the last term here, you only care about those units. The other units here, kind of, this part essentially gets rid of the units. It's kind of normalizing by this term here. And so you can use this essentially as like the, you can use this line as like the center of a cluster, and you can use the distance of a data point as the distance to that line in this coordinate. Right, so you can kind of deal with these things where you have different units in various ways by using this linear regression. It also doesn't care how you normalize the units in each of the other coordinates, because it's not caring about those units to make the prediction. Yeah.
Well, I was just thinking this. I think this doesn't make sense. Actually, now I thought about it, but like, can you just like throw away all the other dimensions and then just like do a?
Yeah, so this is similar to what we talked about last week, Wednesday, where you have lots of these, you're going to have lots of these different dimensions here and lots of coefficients that tell you how important each of those is. Right? And so this is telling you, this A is telling you a model here, and if you're using all of these dimensions, you're building some very complex model. You'd rather have a simpler model. There's lots of generalization properties that we won't really get into in this class. Hopefully the machine learning class will talk about these more. But you'd rather have a simpler model to describe what's going on here. And in this case, that's going to correspond with the coefficients being 0. That means we don't care about that dimension. If I set one of these coefficients to be 0, that means I don't use any information about the second dimension. Okay, and so when doing this compressed sensing, you're kind of choosing these, in some way trying to choose which of those to be non-zero. And we're going to do something somewhat similar with lasso. We'll see. Yeah. So hopefully this will start making sense. Yeah. So this means only important unit in d+1 chord, which equals this y coordinate. Okay, and so you're going to get a function. So this red line here, when I'm in higher dimensions, this is where d is equal to 1. So in the case where d is equal to 2, the red line is going to be a red plane. D is equal to 3, it's going to be a 3-dimensional subspace, and so forth. So I'm going to take all the data. So this dimension is going to be x, and from every data point, I'm essentially predicting a value for the y coordinate. So this is d-dimensional down here. Y is always 1-dimensional. There's a way to do this with multiple y dimensions called multiple regression. We won't really have time to get into this in this class. Okay, so this is the setup. This is ordinary least squares regression. Hopefully, almost all of you have seen some form of this before, even before the preview lecture I gave a couple weeks ago. What we're going to be talking today about is regularization. Okay, and so the idea of regularization, it comes up in. We'll see one kind of one form of how to think about this. You can also. There's a couple of other ways to think about before I can get into it. If you know like these Bayesian techniques, it's essentially some Bayesian prior which is trying to make your model simpler. So if you're using a purely Bayesian approach, you're going to have a prior on your model that it should be simple. And in this case, that the coefficients are going to be 0 is the prior. And how much weight you give them is going to depend on what you use for your regularization parameter. There's another way of thinking about it based on this idea called regression to the mean. So have you heard of regression to the mean before? Okay, so let me try and give an analogy which is not going to be totally fair here. But let's say that to just kind of explain intuitively how this is going to work, and then we'll see how it works with noise in the case of linear regression. So let's say that there's a test that's going to be true, false. And so every student in the class, so let's say there's a large number of students, every student in the class, they know 50 questions, and they guess on 50 questions. Okay, so let's say it's a pretty hard multiple choice test, but everyone, like, for half of the questions, it's really easy, right? Then the answer should be obvious. But the other half, you have no clue what's going on, so you basically make a 50-50 guess. Okay, so if this is going to happen, the expected score, let's say, the expected score is going to be 75%, right? 50% you get right, 50% you get half of them right. Okay, so let's say that I take the top, let's say the top 10% or so of students, and or let's say the top 10 students. Top 10 students, and let's say that their average score, it was 80%. Okay? So the top students did better, right? There was some distribution of students where this was 75%. And so the top 10 students all scored, the average score, let's say, was these students here, the average score was 80, if I look at those top 10 students there. Okay? So now, let's say this first test was the midterm. And so now I'm going to give the final. And the final is just as challenging. 50% of the questions you know, 50% you guess. How do you think I would take, how well do you expect the top students to do? The students who average 80% on the first test. Or not the average, the expected value of top students. What's the expected score that the top students would get? What?
Will it be the same?
They're the same. Is that 80 or is that 75?
Say,
What's which?
8.
80. No, it's going to be expected is going to be of the top is going to be still 75. Because these students, they got lucky in the first test. There's some distribution of the students that's to be expected. The fact that they did well in the first one does not change how they're going to do in the second one. Like if you were flipping a coin instead of, if these students literally flipped a coin on those questions, if they took the final in the same way and they flipped the coin again, their expected value is going to be 75% again, right? So these students are going to regress back towards the mean. Even though they did well at the beginning, their expected score is going to be closer to the mean of the whole class afterwards. Okay? Now, in real scenarios, this isn't quite true. Their students have different skill level, but the ones who do well early, some of that was going to be luck, and some of it is going to be skill. But if I were to look at the top 10 students on the midterm, I'd expect that their average score on the final would actually be lower. On the bright side, the students who did the 10 students who did the worst on the midterm, I'd expect their score on the final to be higher. They're both going to regress towards the mean, which is the 75%. Right? So because this was unbiased noise coming in here, and if I assume unbiased noise from the true expected value, just because they did well early doesn't mean they're going to do well again the next time. Okay, so this is kind of what's called regression to the mean. This comes up a lot in sports. If someone does really well in the first half of the season, they're probably going to do back towards where they usually do the second half of the season. So this sort of thing happens a lot in there. And the same phenomenon is going to occur in linear regression as well. And the rationale is, the idea is I've got this data, okay, and let's say there's some data point up here, and so I fit some model onto the data that tried to minimize all of these costs, but I had this one outlier up here. And if you remember this picture, there was all these x coordinates down here, and I'm trying to predict these y coordinates. And this red curve is predicting these y coordinates here, and I got pulled up by this outlier. I don't expect, so I'm trying to predict if I got a new x coordinate, where's the value going to be? If I saw an outlier in my original data, I don't necessarily expect to see the outlier later. And so it's hard, often you see a picture like this and people draw outliers. The outlier this far up is not really a problem. It needs to be like really, really far up, like a misreading. Often people draw a picture of the outlier down here, and that will actually shift the thing down. You actually usually draw it down here because it fits inside of a nice rectangle, where it's harder to draw one really high up. When really the outliers you're worried about are the ones really far up there or actually really far down here, and you want to bias towards having a slope of 0. That means that the coefficients have no effect on the data. Outliers look like they have a very big effect. You want to bias towards having littler effect. And so that's what regression, the regularization is going to be, you want to do when you're doing the linear regression. Okay, so again, we saw a preview of this, but let's see what this looks like. Again, the first type is called, let's see if I can spell this right. The good thing about spelling names that are Russian is that if you spell it wrong, probably someone else spelled it the same way wrong before. But I think this is the right spelling, but I'm not Russian, so I don't know. So this is called so this technique will be called Tikhonov regularization, or also called ridge regression. And so the idea is that instead of solving these coefficients that just minimizes x, a minus y. So instead of just solving this, right, this was going to be my solution from least squares, and there was this simple closed form way of how to doing it. Right, so instead of doing this, I'm going to add on an extra term here. So I'm going to penalize by this parameter s the 2 norm of the coefficients here. Okay, so if the coefficients are larger, then my total cost, the total cost is over both these terms. I'm going to penalize larger coefficients, forcing them to be smaller. The larger the value s, the more I penalize large coefficients. And so it turns out there's this nice, simple closed form solution here. I do s squared times the identity matrix of the right size and I put it inside this inverse, and I get a closed form solution. Okay? And this is doing what I want to do. I'm making the coefficients are going to be smaller the larger I penalize with this value s. Okay. This is Tikhonov regularization, and so this will make things more robust to outliers. And there's a nice solution to it. But what we're going to talk about today is called the lasso. And so there's, and so this is slightly different. And so I will call this, so A hat S is going to be argument A so this part is the same, but now I'm going to add in instead of minimizing with respect to the 2 norm, I'm using the 1 norm here. Right? The 1 norm is the sum of the absolute value of the coordinates. Right? So this is sorry, 0. It's the sum of the absolute values, where this one, remember, don't need, you can just say AI squared. Okay, that was the sum of the square of the coordinates. Okay, so this seems like a small difference. It turns out this one does not have a simple closed form solution like this anymore. Okay? But it is going to have two. It's going to have two really cool properties, and we're going to talk about these properties. The first one, most of today, and we'll talk a little bit about the second one, and then we'll continue on that on Wednesday. In high dimensions, it's going to bias towards a sparse. So most of this vector A is going to be zeros in high dimensions. And I'll try and explain why that's true. And so it's also going to force to consider the value S. Okay? One thing you should have been wondering is what value of S should we have chosen here? Right? I told you that the larger the S, the more you bias towards coordinates of 0, but I didn't tell you how to choose S. Okay, so you're gonna choose S with cross-validation, it turns out. But the good thing about the lasso, and it's kind of a blessing in disguise, is that there's no simple closed form solution for a single value S. The way you solve it generally is a way that solves it for all values of S's simultaneously. This is called least angle regression, is a version of this. And you solve for all values of S, and so when you're doing that, you can kind of cross-validate as you go. And so you can say which value of S is the best as you're computing them. For all values of S, you can kind of score them, and we'll talk more about that later. Okay? Any questions about lasso or these? The reason why it biases towards sparsity should still be mysterious, but okay. So the next step is to realize that for all values S, there exists a value t such that let me write this up in a slightly different form. Such that okay, so I can say for every value s, there's going to exist a value t such that the solution a hat t is going to be the one that minimizes the sum of the squares subject or such that the norm, the one norm of the vector A is bounded less than t. Okay, so instead of the first value is like a soft constraint. It's not really a constraint, I'm just some soft penalty. This is a hard constraint. I say it has to be less than this value t. Okay, and so how do you see that this is true? As s increases, that means more of a restriction, t is going to decrease. As s increase, then t is going to decrease. Okay? So how do I solve this? Well, if I solve, so t, the t for some value of s is actually going to be the one norm of as, right? So I solve this expression for some value s, okay? And then I take ts. And so I know that this value of as I found is going to satisfy this condition. It's going to be less than or equal to t. In fact, it's going to be exactly equal to t. Right? And that one is going to be the one that minimizes this expression. So I can get this trade-off. So I can write it in either form. And so the first form kind of seems more natural as an optimization problem, but this one will be much easier to think about. And actually the least angle regression algorithm is going to kind of operate by thinking about this value, fixed hard constraint value t. Okay? So what's so special about this? Why does this work? Now it's time for a picture, and I think this is kind of one of the cooler pictures in the class. So hopefully I can do this right. We're going to think about let's draw. So this is going to be the space of A. Okay, and I'm going to bound this is going to be T, so this was 6 steps, okay? Okay, so if I put an L2 constraint on T, if I put an L2 constraint on it, then it's going to look like that A, this vector A, I can think of it in this d-dimensional space, or this d plus 1 dimensional space. So this space here is R d plus 1. So in this case, d was 1 because I can only really draw 2 dimensions. But A is a d plus 1 dimensional vector, and I have a restriction that this is an L2 ball. This ensures, this orange one ensures that A2 is less than or equal to T. Okay? So if A is inside of this orange ball, it's less than or equal to T. If this T is this far, this is supposed to be T, this is a t, and a t, and so forth. Or this was a minus t, but that's the distance from the origin. Okay? Now if I draw an L1 ball instead, how's the L1 ball going to look? People remember? It's the diamond, right? The L1 ball is the sum of the distances, the sum of the coordinates. It's going to look like this, and this ball is going to say that A1 norm is less or equal to t. Okay? So using this L1 constraint fixes that the A vector must lie inside the diamond, where the L2 constraint fixes it lies inside this ball. Okay? So what's the difference? Why is this better? So it turned out that the corners, the blue one, the L1 ball, is pointier. Right? And this is and it's pointy exactly, the corners lie along these axes. And this is what's going to be important. Let me draw another object here. See if I can do this as well. This is going to be, so this is going to be the solution for A with least squares. With ordinary least squares, right? So I just solved the least square solution. I had no regularization term. Okay, so let's say the coordinate for A is like 11 and 3, right? So those are the values I got for A. But that has the norm is too high. The norm T in this case was 6, right? So I'm not allowed to do that. So the solution I'm going to get is going to be the closest solutions for A inside of this space here. Okay, so let's see what that looks like. And the closest in the L2 sense. L2 sense means inside of a ball. Right, so let's first do the closest point to the L2 ball. I can think of drawing a ball around A. It's going to look like this. I'm going to find my ultimate solution will be here. This is going to be A hat of t with the L2 solution, with the L2 regularization. What is the solution going to look like with the L1 regularization, the L1 constraint? I'm going to grow a ball in the L2 sense around A, the least square solution, until I hit this blue diamond. Let me try and draw this carefully here. If I draw it, it's going to look something, it's going to be a little bit bigger ball, because the L2, or the L1 ball is a little bit smaller. The L1 ball is a little bit smaller, so where is it hit? It's going to hit exactly right on this corner. It's going to hit exactly on that vertex there. The closest point is going to be exactly on the corner. And what's special about the solution here? What's special about that solution? What is the y-coordinate of that solution? The y-coordinate 0. Yeah. The corners tend to be in places where the coordinates are 0. Right now, in higher dimensions, this blue ball is actually going to have another pointy thing coming out this way, right? Coming out of the screen here, and more so than just having these pointy things coming out, it's going to have like this kind of edge between here. Okay? If the closest point is on the edge, then it's that is going to have the z or the y coordinate still at 0. the z coordinate will be non-zero. If I'm on a corner, two of the coordinates are 0. If I'm on one of those edges, one of the coordinates is 0. Okay? And so if the true solution is very much further along one of, say, the x coordinate instead of the y coordinate, it's going to tend to make the y coordinate 0. Right? As I rotated this solution up higher y coordinate, these balls are eventually going to start touching along here. And I'm not going to get any sparsity. And eventually high enough that it's going to touch that corner. Right? So when the solution has about all the same coordinates, they're all about the same value, it's going to tend to be dense. But if some of the coordinates are more important than others, then the ones that are less important are going to get zeroed out. Right? So this is why this L1 regularization tends to bias towards the sparser solution. Does that kind of make sense? So one thing maybe you're thinking, well, this L2 thing didn't give me any sparsity. The L1 gave me more sparsity. Why not L0? Right? Remember at some point I tried to draw one of these L0 things, or say L1 half, and it looks kind of like that. And you kind of see the yellow. When you draw magenta, it kind of looks like this is this quadrant of the ball. It's going to be harder and harder, maybe even impossible for some, well, not if you had your true solution was here, that it's hard to get the closest point is in this region here. It's almost always going to be on the corners. Right? But turns out that this would be like L, say, 1/3. Right? The smaller I make that value, the easier I'm going to bias more and more towards these corners. The problem is this shape is no longer going to be convex, and that's going to make the problem really hard to solve. I haven't told you yet how to solve this expression with this L1 constraint. Turns out for L1 there's a nice solution how to solve it. It's a bit intricate. It's not as clean as the ridge regression, but you can do it. You can write, there's code out there that does it for you, and it does it exactly. Right? For this solution, it's going to be a hard optimization problem. There's lots of local minimum. It's hard to solve this. So the L1 serves as the best convex proxy for the L0 constraint. L0 just counts the number of non-zeros. So L0 just penalizes the count of the number of things that are non-zero. The L1 is kind of a convex version of that. Okay. Okay, so hopefully you kind of have an intuitive sense of why this is working. Yeah? I've seen, if you look at other textbooks or other places, you'll see somewhat different pictures of this, but I think this is a good way of seeing what's going on here. All right, so now how would we solve for this solution? Like, how do we write an algorithm that does this? And we're going to do it for all values of s. Actually, we're going to do it for all values of t instead, but there's a way to go kind of back and forth between s and t, or it doesn't matter which one you use. So any ideas of how you do this? What's going to happen if t is very large? If t is really large, so t in this example was like 6 grid cells. What if t was like 100 grid cells? Then what would the answer be?
Same as when you use squares, right?
Yeah, it's going to be exactly the least squares. It's not going to put any constraint on it. And the least square solution is going to be dense. So for t large, you get the ordinary least squares A, which is going to be dense. It's going to be basically all non-zeros unless you kind of get lucky and it happens to lie right on one of the 0 coordinates. Okay, so then what happens if t is small? Very small. What if t is basically 0? What solution are you going to get? What if t is exactly 0? Yeah, if t is exactly 0, then this ball shrinks down to 0, and the solution has to lie inside of it. So your solution is an all 0 thing. Basically, for every input, you're predicting a y value of 0. That's probably not the right thing to do, unless you're maybe a really hardcore Bayesian or something like that. No, that's not how Bayesian statistics works, but I guess you're really strong prior of if you're a very strong Bayesian and you're also a nihilist, I guess. That's probably the right analogy. Everything is 0. Okay, so if t was really small, you get 0. What happens if you make t slightly bigger than 0? What's probably going to happen? You went through a nihilist phase. You're kind of coming out of that slowly.
So like most of you have really sparse.
Yeah.
Very sparse.
Good. So if t is very small, you're going to get, switch colors. I apparently can't write in pink. Very sparse. Yeah. So if t is very small, you're going to get a very sparse solution. And initially, it's going to be so sparse, you're only going to have one non-zero. Right? One non-zero. Okay, so if we were going to pick one of the coordinates to be non-zero, which one would we pick? Like if you saw this picture here, kind of so you're going to pick a coordinate. So we're going to start very small here. So we're going to choose coordinate, we'll call this J1. J1, or J1 is going to be hard max J. So it's going to be the value J which maximizes the absolute value of xj y. Okay, so this is going to correspond with the column of x. Remember, x was all the data points with the one column, right? So maximizes the column J, which is most explanatory, right? This is just like orthogonal magic pursuit, the first step there. We're going to pick the column which is most explanatory of the data. This tells us if we start moving in that direction, if we had to choose one direction to move in, we're going to choose this direction to move in. Okay? So if you're continuing with this nihilist analogy, I know at least someone's hoping I'm going to do this. You're from completely nihilist, one thing in the world makes sense, right? This one coordinate is that thing, right? So this starts making sense. Okay, so you're going to start with that coordinate, and then if you're doing that, your solution, kind of as this ball is growing, your solution is kind of moving in this direction, right? So I'm starting at 0, and I'm kind of moving in this direction as the ball is growing out. I'm moving along the x-axis. Okay, and then at some point, you need to add another coordinate, right? In this example, eventually I get far enough out that the closest point on the diamond is actually going to be not on the x-axis. So we're going to slowly increase t, and as we're doing this, we're going to pick one coordinate, and just like in orthogonal matching pursuit, we're going to be able to figure out what is the best explanation we can get with only this one coordinate. Well, actually, as we increase t, this coordinate is initially going to be t, right? So a of, let's see, oh yeah, this was a lowercase, so this was an element of aj1 is going to be equal to t. As I increase t, the value of this coordinate is going to be exactly t. Okay, and so we're going to think again with this residual. We're going to think about this in terms of this residual where r of t, so this is the residual of what I have not explained left, as a function of t is going to be y minus the sum j equals 1 to d, or 0 to d, of xj aj t. Right, so this is aj as a function of t. That's let me write this slightly differently. aj as a function of t is equal to t. Okay, and so when I only have one coordinate, most of these terms are 0 except for one of them. And then at some point, I need to add one more of these terms. Okay? And this is going to happen at the point where, and so this is going to be a linear function of t up until this point, until some point where, keep doing this until we're going to have xj1 dot rt is going to be equal to xj2 dot rt. Okay, so when this term, which is the first coordinate we found, is going to have the same kind of explanation power of the residual of another term, j2, then this is the second coordinate we pick. And so if you think about in this picture, what's happening here is eventually, if I draw the closest point in the green circle, which is going to be shrinking, my air, because of regularization, is going to be shrinking as the solution I allow gets bigger. Eventually this diamond is going to be such that the closest point in the green circle is going to touch not on the vertex but on the line there. And then there are two coordinates equally explanatory. And so at that point in 2 dimensions, these coordinates are going to have equal explanatory power. And so at this point, you're going to have then, you're going to have this, so after this happens, you're going to have I'll try and write this down and then it's going to look like confusing initially and hopefully not stay that way. aj minus 1, or aj1 at some specific time t2. So this happens at time t2. This happens at time t2. plus t minus t2 times b1 and aj2 of t is going to be equal to aj2 up. It's going to be t minus t2 times b2. Okay? And I'm going to have, so what's happening here is now I'm getting these two coefficients are going to be non-zero, and they're growing linearly with respect to this parameter t. And so basically this first one grew until time t2 when I found the second coordinate, and I had this value, and then it's growing at the distance from time t2. So as t gets bigger than t2, I've grown more at this fixed rate b1. And similarly, after time t2, this one is growing starting from 0 now at a fixed rate b2. And I have to have that the sum of the absolute values of b1 and b2 is equal to 1. Because as I'm growing at the rate I'm growing t, I'm distributing the growth among both of these two terms. Okay, and kind of working out how to solve for b1 and b2, you can do, but the important point to realize is that the growth is linear in both of these, so this expression is still a linear expression of t. Every time we find one of these events that's happening, where these absolute value of the dot products are the same, I'm getting a kink in some linear curve, but in between it's linear, and because it's linear, you can always solve for when this next event is going to happen. Okay, and so now there seems to be lots of technical details you have to work out, but hopefully you can believe that something like this can be done. Okay, and if you look in the notes, I've written out some pseudo code saying how to do this in more detail, but this is kind of roughly how it works. So I also linked on the webpage, there's this book which is freely available online called Elements of Statistical Learning by a bunch of few statisticians out of Stanford, and it has like maybe 50 to 100 pages on this in much more detail. Not just this algorithm, but explaining this whole effect, and then it does a lot of cool stuff beyond this. But so there's a way to solve for, and so if you want to find the coordinates for a certain value of t, then you're running this process, you keep increasing t, and you find these event points, and you grow all of the coefficients, however many are active, at some linear rate, and eventually you hit the value of t that you want, and you stop. Right, so, okay, so again, what value of t did you want? Well, the good thing is you solve this in the process. You solve this for all values of t, basically until things stop improving. At some point, your ball includes the least square solution, and all these coefficients essentially kind of, all of these inner products are at that point become 0 because the residual, there's nothing left to explain. Because this residual becomes 0. Or at least it, yeah. So you should probably stop before you get to the end. But you've solved this for all values of t, which implies you've solved it for all values of s. So now you can go back and look and see which one you want. Sometimes you'll do it based on cross-validation. Sometimes you'll do it, say, I only want 6 coordinates. Right? After I get to 6 coordinates, I'm going to wait maybe right up until I get to 7 coordinates. I'm about to get to the 7th one, and I'm going to stop right there when I only need 6. Okay. There are, I've got a weird page boundary here. So this process, which I kind of sketched over here, is called, this process was called least angle regression. So there are a couple of things worth pointing out. values of AJ can be negative. Okay? This should make sense. If you're doing linear regression, values, your coefficients, they can be negative if that coefficient is negatively correlated with what you're predicting, right? What's strange is as you progress t, as t increases, value of AJ can oscillate between negative and positive. Okay? So it can oscillate between negative and positive. This should seem like a little bit unintuitive. It means if it starts growing positively, it may not always grow positively. It seems that this becomes, if there wasn't this least angle regression is a pretty clever solution because there's lots of local minimum that could be kind of going on here. But it turns out this essentially is giving you the optimal solution. There's one trick I didn't mention, some detail you have to do. What can happen is as it goes between positive and negative, when it hits 0, you want to snap it to 0. So you want to say if AJ hits 0, then snap. Okay. Snap. And what that snap means is that if you're going to move it away from 0 again, you need to re-encounter one of these conditions with that coordinate. So you're unusing that coordinate. You no longer use that one anymore. Okay, so what's kind of going on here is that you could think of there's one variable which does a pretty good job of explaining some phenomena by itself. But as you get a better model, there are two other variables which combined do a better job of explaining it. And in fact, if you have both of those, you can get rid of the first coordinate. You can get rid of the first variable. This can happen. Right? So this is related to this effect called collinearity, where the second two variables kind of had within their span, or very close to their span, the first variable. It didn't add a lot more to it. But if you're only to use one of them, it was doing a good job. Okay. Okay. So if this happens, it's snap. So that means you then only change AJ if you get if you get this condition again. If you hit this condition with AJ again, that's the only time you remove AJ from 0. So sometimes it will come, hit the line, and then at some point later go back up or go down. Okay, so this makes it a little bit messier. If you didn't deal with this case, then the first approach was actually you can get to run, I think, in linear, in basically linear time in the data. But with this condition, you can actually go through some exponential number of different subsets. And so the runtime becomes it's no longer a polynomial algorithm. But you need this one to get the exact answer. For a long time, this was conjectured to actually have a linear number of times this could happen. But there were some really crazy examples that showed that this doesn't happen. This could happen an exponential number of times, but it usually doesn't. So if you have an implementation of this, probably use it and not worry about it, but kind of worry about it. If things are not going right, then kind of say, the other one works well enough without the snap. what else do I want to say? So, okay, so we're gonna jump. I'm gonna spend a lot more time on Wednesday about cross-validation, but let me just say, in what sense? Let me just try and get across kind of this point. Is this better than ordinary least squares? So I said this was going to be more robust to outliers, but ordinary least squares was the best least squares fit. I fit my data the best way possible. So is this way that's regularized better than least squares? In what way is it better? Yeah.
So it's like better if you're gonna see if your training set doesn't generalize well to like the new data that you're gonna see, then this model will be better.
Yeah. Okay. So good. So I'll try and re-explain this. So this is we're going to look at something called the generalization error, and this is kind of a different way of looking at the error. And under this generalization error, there's going to be some S or T parameter which is going to do better. And so the way to think about this as your data, this is D plus 1, and you're going to, and this is going to get into doing cross-validation, but you're going to train on this data, right? This is through N1 or N. So the number of training data you have. So this one is going to build a model A. So this is our data P here. I'm just going to build a model A. And then what you want to do, you want to measure the error, and we'll call this, this was P, and then you have X, where this was the Y coordinate, and so this is like missing. You want to say from this X test times A minus Y test. You want this error to be small. Okay, so I train on the data up here, but then I want to evaluate it on this other data I haven't seen yet. So if you're just trying to see how much error do I have on my training data, you can't beat ordinary least squares in this sense if you're measuring this sum of squared errors. It gives you the best optimal fit for that data. But if I want to train on new data, which is the whole point of this, right? I want to take some data, build a model, so then when I see something new, I'm going to make a good job of predicting what's going to happen, what the value is going to be. Then that is being simulated by taking the data set and splitting it into the training part and the testing part. And it's in this sense that doing this regularization is going to do better. And this is true both for the ridge regression with this easy to solve least L2 regularization, as well as this lasso, which has the L1 regularization, which is going to be harder to solve, right? So they're both going to give you a better solution in this sense. It's not clear what value of S to use, right? You're going to do this for some value of S. Right? And if S is equal to 0, then this is exactly the least square solution. If it's something else, then you're going to get that, right? So you're going to get some errors of function of S, and you want to find the best S here. And so essentially finding this best S is what is cross-validation. And we'll talk more about that. But if you want to prove improvement bounds, then you have to look at it in this regime. And this is really what tends to matter. Okay, so that's all I have for today. So we'll talk about cross-validation and noise of all sorts of kind of views of noise starting tomorrow, Wednesday. And then next Monday will be a really fun lecture on dealing with privacy and data. There's like, if you're part of this big data certificate, we agreed to every class part of it should have some ethics component. And so the next Monday is kind of the ethics lecture by viewing it through privacy, and I'll give some stern warnings about what not to do as part of that. Hopefully it'll actually make a difference. So it'll be fun. All right, so I'll see you on Wednesday. Hopefully we'll get the feedback for your project intermediate report and the next homework out soon.